Okay, well, welcome everyone who's attending this talk in the room and from home. That's a new thing for us. We tried a few weeks ago, but it didn't go as well. So we're very happy to have here Moritz Schauer. He's a associate professor at here at Chalmers and Göteborg University in the mathematical statistics. And we have been colleagues for 3 years and co-sharing the same corridor. As you can see from Moritz's face, he's not super happy about that, but I'm joking, of course. And today's talk is focused on this relatively new class of Monte Carlo samplers, the sticky Zig Zag sampler, and particularly for the target of doing a variable selection in a Bayesian setting. Okay, so I think Moritz, whenever you want, you can start.
Yes, so thank you for the introduction. And yeah, so this is something I really started to like working on maybe 2 or 3 years ago only. So this was a new topic for me also recently. And so I have done before quite a bit of Bayesian inference for stochastic processes using Markov chain Monte Carlo. So I was looking at various different processes, but to do the inference, I was looking at Markov chains. And then I learned that you can also think about the other side. You can ask yourself, what kind of process am I using to do the Bayesian inference, the sampling of my posterior? And there are new interesting approaches. And one of these approaches I want to talk about, and I want to talk about how we extended it to the problem of variable selection. So just to pin down a bit of my notation, I have here, there's some probabilistic model in the background, which gives us a parameter vector. The vector here, the parameters are x and not theta, and then there is a likelihood function, and I don't put the observations into the likelihood function. So typically you get some observation and then the likelihood function will depend on that. But let's just write it as a function of the parameter and have the observations hidden in the background without a letter. So if you do Bayesian inference, then Bayes' theorem gives you a posterior distribution to sample from. So somehow the posterior distribution induces a measure, mu, a normalized target measure with some density you want to sample from. And you want to say, yeah, a density, you have a bit of freedom, right? So typically, if you have a probability density, then the thing you're used to is to express it as a density with respect to the Lebesgue measure or the volume measure in space. So you write down f of x is the local ratio between the probability I'm charging on an infinitesimal area divided by the volume of the area, and that's then in the limit, the local density. But you can also take a different reference measure. You can take a different frame of reference and, for example, express likelihood or log likelihood as the log of the local ratio between prior and posterior. So just to get you a bit used to my notation where the d-axis are infinitesimal sets, the probability, the volume, the posterior, and the prior are all measures, and then the fx and the lx are functions. And the symbol on the bottom, which looks like an 8, is the proportionality. So the exponentiated log likelihood is proportional to the posterior times the prior times the log likelihood is proportional to the posterior. So if you, having said that, so then coming back to the initial problem, so we want to sample from a posterior or just to measure mu, and that's either as in the previous slide, the posterior with respect to the prior, or in general somehow the measure we want to sample from, and we could reparameterize it and express it as this exponential of minus a bit like the negative log likelihood, but a minus function of psi x times a reference measure dx, and the reference measure mu0, that could be the Lebesgue measure in normal cases. So just to set the scene, this is the notation I'm going to use. But now let's talk a bit about there's a question. Ah, yeah, that's you. So there's a different way. I told you that I got interested in doing the sampling from the process. So just computing something which is proportional to the posterior density, which is proportional to the posterior, doesn't actually answer our questions we have as statisticians. So we would rather have samples from that distribution, because only if we have the samples, then we can make some claims about what's the probability that certain parameter is larger than 0? What's the probability that if I'm not know which model I should take, what's the probability of that model, etc. And so just to get you introduced to the topic, so what you're here seeing is a very simple problem. It's just sampling from a Gaussian distribution. The density is drawn, maybe centered at point -7.07, etc. And so you can already start thinking, what's the difference between a Markov chain, which you would use to sample this distribution, and here the piecewise deterministic Markov process, which I'm going to introduce you on the next slide. So, and apparently I have a particle which moves through the space in a continuous motion. It moves straight until an event happens, and when the event happens, it changes direction. And then in light blue, you see in the background the occupation measure of this particle. You see this histogram, which if you continue to follow the trajectory of the particle, then the time the particle has spent in each of possible intervals of the axis x. The axis I'm interested is the axis of the parameter, or the place where this posterior measure is defined. Then this histogram approaches the density we want to sample from. And if we want to have a question like, what's the probability that my parameter is larger than 0, we can translate it into what's the fractional time my particle has spent in the right half of the real line, has spent above 0 in the real line. So we can answer with that our statistical question. And my focus will be a bit of variable selection that would translate how much time my particle spends close to 0 if 0 corresponds to a variable not belonging to the model. So piecewise deterministic Markov process. So what's in there, it's a Markov process. So without memory, what's doing in the next moment is only depending on where it's currently are. And then piecewise deterministic for certain time intervals, it moves on deterministic trajectories. So that deterministic part is just what you see here, that this particle moves on a deterministic line until randomness comes into play, and the randomness just changes directions. So what I already said in words. So we have this process xt with real time access, and it's in the Markov chain you would have a process xi for I is 1, 2, 3, 4, so just samples. But now we have a continuous process, and we want to use it or some ergodicity result to answer questions about our posterior mu. So for example, the probability that my posterior charges on set A, I can approximate, or I can compute as the limit of the occupation time of my process. So this is the indicator function of xs in A, and there's 1 divided by t missing here, sorry. So the relative time I'm spending in the event. So how do you construct a piecewise deterministic process which has a certain distribution as its target? So we have a distribution mu and we want to sample from it. So you start with, in a Markov chain Monte Carlo, you start with a Markov chain with transition operator Q, and then you change it into a Markov chain which actually samples from the distribution you want. Something similar here, we start with something simple, which doesn't yet sample the target distribution. It's just deterministic dynamics. I have a particle moving on a straight line through space and disappearing. So that doesn't even have a stationary distribution, but at least it has, you have this notion of, if you look at the occupation time, it's flat, and you could think of it as preserving the improper uniform distribution. So it's something very simple. So if you are in the, I gave part of this talk to the Julia con, but there I left all the mass between the slides. So now you're getting that. So I have this augmented state space where for each coordinate I have a position xi and a velocity vi. And then if I have many coordinates, I have this product of coordinate spaces. And I equip this with a very simple motion, for example, linear motion, which preserves the background. The reference measure mu0 would be Lebesgue measure here. So each coordinate independently changes according to its speed variable, and the speed never changes. That would be the most simple thing, but you can also do some nice things. For example, you take some simple Hamiltonian system which preserves a Gaussian distribution. Then the speed would change depending on your position. You have some pendulum as a ordinary differential equation there. And if you we take something easy where we can write down the solution in closed form, because we don't want to spend time solving this proposal process. That should be easy. So here I just give this trajectory, deterministic trajectory. If I'm in UI at time s, then I can compute where I'm at time t by just following this flow function. And the important thing a bit is that this flow function, we can compute it for each of the coordinates separately. So the next thing I want to introduce is, it's very nice for later to be able to answer the question how a test function evaluated in my current point changes over time. And this operator x is the derivative of that. So the x applied to an f tells me the infinitesimal change I have under the flow if I'm using a test function f. And in our case here, well, it's a linear motion, so I'm just moving in some direction. Then my infinitesimal change depends on it. It's essentially the dot product with the gradient. That's the linear dynamics. And this x operator here, the script x or Gothic x, that describes the motion here. So from the x, you can recover these two laws if you want.
Sorry, Moritz, just what is this phi actually? Function phi?
It's a function you plug in. So you're currently in position u at time s. You want to know where you are in, what the position u at time t is. So you solve the ordinary differential equation system and give the solution a name, and that's phi. So phi is the name of the solution or the flow. So the next thing is, this is the wrong distribution, right? It preserves the wrong measure. So we have to add something, and that corresponds to accept reject step in Metropolis Hastings. And we don't have an accept reject step, we have a reflect step. So at certain points, before we are moving too far in the tails, we are reflecting, and this the probability with which we reflect in the next time instance, if we tune that right, then we can change the distribution from the flat improper on the line into the target distribution. So let me give you how to choose that actually. So essentially, if you want to have your process to be a Markov process, then there's only the direction changes have to come at Poisson times. So essentially, the time to the next reflection in coordinate k is given here by the probability that an inhomogeneous Poisson process has. So on the left-hand side, you have the probability that my reflection time is larger than t, and on the right-hand side, you have the expression you would get for an inhomogeneous Poisson process that the next event time is larger than t. So this is the integral over intensity function lambda k, which tells you for each point where you are. And notice that here we are just deterministically following the flow. So we are currently in some position, and then we see where we would move conditionally on not having any reflection at all. And for each of the points we visit, we have this local intensity, the local density or probability to have a reflection. And so this gives us the new reflection time tau as the minimum of all these possible reflection events. Note that my pictures are one-dimensional, but you have a multi-dimensional problem actually. So your next time is tau. You go with that, then you get a deterministic trajectory until time tau. And exactly at time tau, or you look what the what the limit is, so just a second, just an epsilon before tau, and then you apply appropriate jump. Yeah, you don't see the jump because it's a jump in the velocity variable and not in the position variable, but it's just a jump kernel, and the jump says, yeah, change the velocity, flip the sign of the velocity in coordinate k. And I have this private notation for that. So this is the vector k with coordinate k replaced by minus vk. So that was a deterministic change, but you could also think of some random rule which takes in high dimension a random reflection or something. And then you would have a transition, a Markov kernel, which tells you your new position given the limiting position from which you arrive. So I think I made the deterministic dynamics green. Now we have this at event times, you have a change, a jump, which is blue. And let's just talk about how this lambda, the lambda is the intensity of the jumps, how this exactly should look like. So I have here just an example. You're having these times from the Poisson process. I'm taking something which I'm going to explain later, but essentially I'm proposing times and I'm not reflecting at each of these times. But at some point I'm proposing a time where I'm reflecting, and then the process changed the direction. And so the direction change will happen depending on the gradient of the minus log p. So to be precise, this lambda I, which gives me the instantaneous probability of reflection in point xv, that's the maximum of 0, so truncated at 0, the velocity times the gradient, or the partial derivative. It's the ith element of the gradient of this function psi, which is the negative log density between mu and mu 0. So you remember this from the first slide, but maybe let's go back. So I have this parametrization where I write my target measure as x to the minus psi x times the reference measure. So that's the density. So And then I can characterize this entire Markov process, which piecewise deterministic movements, and then changes at random times by its again behavior, infinitesimal behavior on a test function. And then I get the operator I started with, that was the deterministic dynamics, how f changes under that. And this is how f changes under my jump corner. So if I'm doing a jump from x and v to x prime and v prime, then my function changes from x, y to f x prime, y prime. And then the lambda is the intensity of the change. And that in total characterizes my stochastic process x comma y, v. And you can make this formal that you get this operator as time derivative of an expression which you can understand as comparing the function in the point where I am with the expectation of the function in a point I'm in a later time divided by time, so it's a time derivative. So one classical piecewise deterministic Markov process is to sample distribution is the Zig Zag sampler. Just if you want to see this for a second. Yes. So the state space is the product of x as my parameter, and I take the product with two possible speeds, -1 and +1 are two choices for my speed. Then my target measure, that's actually, it must be a product between my measure on the parameter and the measure on the speed dy, dv. And I say that this is proportional to so the target measure, and you see that this is uniform in my speed. So the direction of the process doesn't change the distribution. I have this deterministic dynamics where x changes by v and v doesn't change. I have, as you have seen, this lambda, which depends on the target measure. My transition kernel, it's just flipping the v coordinate, so it's a Dirac measure. And I can write down the generator, this infinitesimal description of the corresponding Markov process. With the colored ingredients, deterministic flow, intensity of flips, and the way the flip looked like. Okay, so this is, I have a process. How on Earth can I show that this preserves my measure mu? Or the measure mu times nu, if nu is the uniform distribution on the speed vector. So the idea is that it's actually easier for a continuous time process than for discrete time processes, because you prove that the process x preserves the measure for an infinitesimal time. So what you can read here is you look at the expectation of this test function and how it changes for a very short time when you're currently in a point xv. And you assume that this point xv is drawn from the stationary distribution. So then if it's drawn from the stationary distribution and you move a little bit, you don't expect it to change. So on average, that should be 0. And indeed, that gives us a condition, which I only motivate here, but essentially you have to look at this operator A, which is infinitesimal. And not so ugly if you go back here. This is just taking derivatives and looking at a function and how it flips. And then you have to check that it is on average under the measure mu, that it is 0 for a large enough class of function f. So the f's on my test function, if I test for enough function, then then I'm good, and I have established that my process x has mu as stationary measure, and I can use it to sample. What we have not used here, so what didn't we use? We haven't used detailed balance, right? So we have constructed a process which doesn't have actually detailed balance. It has something like skew detailed balance. And why is it nice that we did not use detailed balance? Because detailed balance is essentially when you use Metropolis Hastings step to get a process which has detailed balance, necessarily you're introducing random walk behavior. So your process steps in one direction, forgets in where it came from, and then steps in a random direction. And if you constantly forget where you came from, then it takes you quite some time to explore an area. And we have this a bit nicely that you're moving through the space with momentum, and then you're changing the direction, but you're never, so your Markov, of course, but you don't have this property that wherever you go has the same probability as being there and coming from there. Okay, so all together now, then you get this process with the deterministic dynamics. And then you reflect, and you see that it moves through the space until it hits the tail. And only if it hits the tail, it has a reflection event. So as long as it is moving in the right direction, it never reflects. So as long as it's moving towards larger mass, it does not reflect. That's the maximum in this expression for lambda. And yeah, so then how to use this in Bayesian variable selection. So I just want to introduce a Bayesian variable selection problem first. So I have here a picture, and you can see what's on the picture, right? But I observed this picture in noise, and I want to teach the computer how to compute the posterior here. So that's, let's say, 100,000 pixels, and then a small connected region contains a signal of interest. It's observed with independent Gaussian noise, and I'm interested in this signal. So if you want to write this as a model, then I can write that my observations y, they are for each pixel, I have this variable at coordinate I, j, and I say that what I'm observing is the actual pixel color xij plus some noise. And then I, j is from 1 to n, so it's an n times n picture. And then I want to formulate it as a Bayesian variable Bayesian problem. So I want to sample a posterior, and I write again my posterior as in this form. And now I want to choose a nice prior μ0 on these axes to make my problem well behaved. So a priori, each of the pixels is 0 with high probabilities because there's only a small region with signal. So the way to encode this as a prior distribution is we're just doing the literal way. We take some continuous component, some density on the real line, and we mix it with a certain fraction of a Dirac measure at 0. So the delta is a Dirac mass at 0. And depending on your weight W for the continuous part and the weight for the Dirac part, you're making different statements. So 1 minus W is the a priori probability that a pixel is 0 or that a variable does not belong to your model. So you could think of why do I want a Dirac measure there? I could approximate my Dirac measure by a very spiked continuous measure, right? But that's not. So if you do this and then you have a gradient-based sampler, then it will do a lot of work at the spike because the gradient is relatively large here, so you cannot move for a long time in some direction. You will have a lot of events, and also if you would do Hamiltonian Monte Carlo, then this the sampler would have troubles with the continuous approximation to a spike. So, but we can play with this measure μ0. So we don't have to. We don't really have to preserve a Lebesgue measure. So now I have a deterministic dynamic, and then I spend some time in 0, and then I continue. That was a bit fast, so let's just look at this. As I have this dynamic, I'm moving through space, then I spend a random time in 0, and then I move on. So that preserves an uniform atom at 0. So I have again, so now we call this sticky because you're sticking to 0 for some moment. So you have your linear flow as before, it's just linear movement. When you hit 0 in a coordinate, you freeze. That means that you temporarily set your speed in that coordinate to 0. And you can compute ahead the time where this happens. So you have this deterministic dynamics, and you know, okay, if I would continue for so many time in that direction, I would hit 0. And then you freeze. And then you want to unfreeze in a Markovian way. The way to do it is to have the probability to unfreeze that's happening at a certain rate, at a certain Poisson rate. And that means that you unfreeze after an exponential time with rate kappa. And then you can relate the rate kappa to the W on the previous slide. And we need reflections. And that's nice. We can still use the same intensity for the reflections lambda, and that gives me a sampler with the right target measure. And now you see, so I'm moving on the deterministic trajectory, having my reflections. Every time I pass 0, I spend some time there, and then I continue in the same direction. And there's no work required for that. So I'm just spending a fixed time in 0. So a fixed random time from a fixed distribution. And the singularity is sitting in the reference measure, not anymore in the target measure. But I have a deterministic dynamics which preserves that reference measure. So you have to do no change of measure to get away from it. I only have to change the continuous part through reflection. I don't have to change the direct part. Yes.
What did you actually mean with I have to spend a fixed but random time at 0, which I find counterintuitive?
I corrected me. I spent a time at 0 drawn from a fixed distribution.
Thanks.
Thank you. So, and then don't read the first bullet point. I say in words, it's not so difficult. You have the same way of writing down a generator for this process. And essentially what's happening, you have the this part, and that part is just what you had before for the Zig Zag. And then you have a special rule that every time you hit 0, you freeze there. And then if you're frozen, then you need to spend some time there, and that says you jump with a certain probability away from that, which depends on your rate kappa. And if you want to get this right, so how do you do this in a Markovian way that you're moving forward, you're hitting a point, you're spending time there, and then you're moving away? If you want to do this in a Markovian way, then you have to remember whether you just came into the point or you're already spending time there. And the only way to get this in a Markovian state space is by making a copy of the point you want to wait at. So essentially my state space then is not anymore the real line, but it's 2 half-open intervals which contain 2 copies of 0. And once I'm hitting the 0 in one interval, I'm jumping to the other 0, spending some time there, and then continue. So just looking again, so my trajectory in Markov chain Monte Carlo, you would jump around in space at discrete steps. And for the sticky Zig Zag, you're moving on these deterministic. Now I have a time axis and a coordinate axis. You're moving in some direction at some random point. At random time, you have a reflection event. And then you hit 0, spend an exponential time there, and then you continue in the same direction. So even if you spend time in 0, you continue after you spend some time there. Your movement in the same direction. So you keep the momentum even when you're making a break. Okay, and how do we know that this X leaves mu invariant? Well, the basic idea is you show the same thing for that particular measure. So that's also maybe I could say why I have this density or minus log density psi here, so I can put some parts of the continuous parts of my reference measure here are also absorbed in the psi function. So this is both prior and posterior, except of this Dirac part. The Dirac part is sitting in the reference measure. So I have to look at how this operator acts on a large class of functions, and that gives me the right result. And this is the way we show that our process preserves the right measure. Yeah, and here I have this relationship between the weight of the component and the Dirac part, the intensity of weighting at 0, or the intensity of stopping to weight at 0, to be precise. And here it's you can also add different components. So if you want to also have a prior which tells you how the continuous pixels are related, if you want to have a smoothing prior, for example, some Gaussian smoothing prior, so that you that would all be things you can absorb in this density psi. So that's also something we're going to do. So here I have this image data, and this is my initial configuration of my sampler. So you're looking at the height in this picture tells you the location of that coordinate which tries to recover the pixel color. So these pixels here have a light color, so my coordinate is high. Just an initialization from some it's just a Gaussian smooth. So it's actually the observations maybe itself. And then I'm running the sampler. And you see that each of the coordinates, they're moving up and down, and when they're in 0, they spend some time there. And that gives me the posterior mean, or that's, I think, actually the marginal posterior media. I have to check. But you see that I am having close to 0 estimation error on the black pixels, because my prior tells me that with high probability my pixels are black. Most of the pixels are black. So and my posterior gives me that back. So I'm using a spike and slab prior here to regularize the problem, and the problem remains to estimate the heart, the surface of the heart, where the heart is located. But I'm also doing good there because I have just a Gaussian smoothing prior. So at this point, this is joint work with Joris Birken, Sebastiano Grazzi, Frank von der Möen, and we put they are all in Delft, and we put the paper out sometimes earlier in this year. And so I have only shown you how to make the Zig Zag sampler, the one which has this coordinate-wise linear dynamics, how to make it sticky. But you can also do similar things to other piecewise deterministic Monte Carlo samplers. And so there are some nice extensions, but I think okay, so just a teaser picture. So there's a lot of things going on, but you can see that it's a 2-dimensional problem I'm sampling from. I have every time in one coordinate I'm hitting 0. So if my trajectory comes here, then at this point one of the coordinate would be 0. And that means that 6 to 0, it would move for a short time on this line, and then unfreeze and continue the movement. And there are some other things going on. So, for example, that the density vanishes towards 0 in one coordinate. There's a jump in the density at 0.5 in a coordinate, etc. So, the sampler can be extended to deal with these cases. Yeah, and then there's a boundary, and what happens at the boundary? That's probably easy to see. You just reflect at the boundary, and that is the right movement to preserve the target measure again. So here, the list of evil things from this teaser. And we can sample it. So I want to make a bit advertisement. So the code for sampling these processes is contained in Sebastiano and my Julia package, Zig Zag Boomerang. So yes, so this is our package here, and if you have the name, then it's also straightforward to install. So here you see this is fresh work. So we started working on this 2020. And it's nice because it plays nicely with probabilistic programming languages. So you can use, for example, in Julia of Turing to describe a probabilistic model. This looks like a binomial regression model. And then you define your model using Turing, and then you use our sampler to sample the posterior. And well, this is the posterior. You should get suspicious. Is this a posterior sampled by a piecewise deterministic process? Looks like points, right? But I just subsample, so I'm following this trajectory, and then I keep some subsamples. And similar, just for fairness, I have one example with Turing and one example with SAS, both packages for writing down probabilistic models. And this is one where you define a spike and slab prior on some distribution as a mixture of a normal and with a certain weight, and then a Dirac mass at 0. And this looks like a Gaussian regression model where you're unsure whether the coefficient alpha and beta belong to the model or not. And again, you can sample this with the sticky Zig Zag, which is included in the package. And if you look into the main implementation, so you have these event times which tell you what happens next, and then you keep track of in which coordinate I have to do the next reflection by keeping everything in an efficient data structure, which is essentially event queue. So I have these. I like to. So I want to use the last bit of time to talk a bit about some nice properties. So it's all very nice. So I can do this. It's performing well. So we are, I think, very competitive compared to other approaches, especially Gibbs sampling. And one of the reasons is that we have this non-reversible or the dynamics which do not follow a detailed balance. So we're moving through the state space relatively fast, and then we don't have to, then we typically don't get stuck in small random exploration of some corners of the state space. And then the next thing, so the next thing I think I illustrated that you can combine this with things which often are rather difficult. So how do you deal in Hamiltonian Monte Carlo with a restriction on the support on the target measure with a discontinuity, etc. But essentially with piecewise deterministic Monte Carlo, because you always can predict a little bit ahead when things of interest happens, then you only have to react to the boundary exactly when you hit the boundary and not in the neighborhood of the boundary. Okay, so one nice thing we can do is if you have a target measure which is factorized, so it's a product over a component. Each of the components is a density function depending on only a few of the coordinates. So this is X subset to a set of coordinates A, where A is over all factors you have. And then normalized by the partition function. So if you do this, then your likelihood, the log likelihood will look like sum. And the product comes sum, and each you express it as a sum of these factors, and each of the factor depends only on a few number of variables. So if you remember what the lambda was the maximum of 0 and then the derivative of the psi function. But if you take the derivative of the psi function, or here for illustration, the derivative of the log likelihood with respect to some coordinate, then you only have to look at those factors where this coordinate actually shows up, and ignore all the others. So you can ignore the factor 1 because it doesn't depend on x2. That allows for nice locality and efficiency. So you're just having sparse computations. So you never have to look at the entire posterior. And one nice thing is if you use a probabilistic programming language, they actually keep track of this local dependencies, and they can tell you if they care what the factorized model of this model is, because they are building up the tree of dependencies anyway. So we are working on making that connection too. So it would be very nice if we can use that information about the factorization of the model automatically. Yeah, so then one other remark. So you had this need to sample the reflections. And you have already seen in one of the illustrations that I was proposing points and then accepting them as a reflection or not. And that's called Poisson thinning. And essentially, if you stay in my notation, then the intensity you want is a function lambda of I along my deterministic trajectory starting in my current configuration. And then it's u of a because my lambda I will only depend on a few coordinates. So I have to look how my flow in these few coordinates A continues in order to decide when my next reflection event for coordinate I is. So I is the coordinate in which I want to reflect, and A are the coordinates I have to look at to make that decision. So I look at the flow, and if I can upper bound it by a simpler function, at some point I have to sample the Poisson process, and if I can upper bound it by something simpler, maybe even just by a constant, then I can use Poisson thinning to get the next proposed reflection times. And there's something nice here that the but maybe I'm going a bit too far ahead now, that you can that you have two notions of locality. One is the actual target measure, the factor graph of the problem, and one is a simplified measure of locality, which is the locality of your bounds. Could be that the bounds just depend on anything. You just take a fixed number, for example. So the text was, so you need to know where your neighbors in a second factor graph are if you want to decide about the upper bound, and then you just have to check. Then the decision rule is you reflect actually with the probability will be lambda I over lambda I bar. That's why you need lambda bar to be larger. So, and then yeah, if you work everything out, then you get a nice algorithm. And the only interesting part about it is that we have written it down very carefully, and that you only have to do local manipulations of your state. So you have this huge vector, which is your state of your sampler. But essentially, at some points, I'm only asked to update all coordinates I need to know to compute my next reflection time for the coordinate k. And that may be only 5 coordinates. So I have these local operations. Yes. Yes. So one last thing is what we have introduced. So you have these upper bounds, you want to sample from it. And one of the problems to make this practical, so you want to have what Umberto would call plug and play. You don't want to look for these upper bounds yourself. You want to compute them automatically. And the way we are doing is we are trying to find upper bounds which are only valid for a short amount of time. So we have our target lambda I, and then we upper bound it by a lambda bar. And if we only want to have something which is an upper bound for a very short time, then that's actually something we can do automatic. The way we think of it is you have your inhomogeneous Poisson process with intensity lambda you want to sample from. You're currently somewhere here. You want to have an upper bound. Well, if you have automatic differentiation, you can just compute the local linear approximation to it, and then use the local linear approximation for a certain time interval. So then let me come to the conclusion. So we have seen different, so we have talked about piecewise deterministic Monte Carlo processes. We have seen different exciting extensions about this. I have talked in particular about our sticky extension, which does the variable selection problem. And I have these different requirements from the boundary of the density, from my Dirac measure in the prior, from discontinuities in the density. And one of the nice things is I can combine these because I'm just checking what is the next thing which will happen and how do I have to take it into account to preserve balance. So I have different things and I can easily combine it into a joint sampler. And so we essentially, it's very easy to extend the sticky PDMP to some other things. So there's some ongoing work about how to do these discontinuities. There's some, we have these local bounds using automatic differentiation. And then the main paper, that was the sticky zigzag paper I already gave you. And then the local property that the zigzag has these nice properties if you have a structured target density. That's something we already did in an earlier paper on doing piecewise deterministic Monte Carlo methods for diffusion bridges. So thank you for your attention.
Thank you very much, Moritz. Before going to the questions, I stopped the recording.